cameras in your seat pan if you need. No, I don't think I can't take pictures of the penetrometer at the same time. Go ahead. Sorry about that. Dave, you'll get a warning horn and you'll want to go over to your own.
So NGI is in the middle of a project where we have been asked to design what's known as a cone penetration test calibration chamber. The idea is that we are going to create some infrastructure that we'll host here at NGI that can be used to test geotechnical and geophysical instrumentation that might be used on the moon someday. Right now is phase one of the project, where we're just designing the chamber itself, trying to figure out what it takes to replicate the lunar environment here on Earth. And in phase two, if it goes forward, we'll be building this in the next few years.
Well, why do we actually need a calibration chamber? What we want to do is simulate the conditions on the moon and then be able to calibrate those conditions to do testing afterwards. What we want to do with a calibration chamber nowadays is to apply the conditions that are the moon as best as possible, which means we need very cold temperatures, very hot temperatures, and we need vacuum as well. Vacuum will complicate some things on the calibration chamber because there is no easy way to just apply vacuum without freaky things going on inside the lunar soil. What is going to happen is all oxygen or gases inside start going to be boiling inside the soil. So when we apply the vacuum, suddenly you see all this gas popping around, and that takes time. It's going to take sometimes even days. And it's something we need to do if we want to really come as close as possible as the conditions on the moon.
So we are of course talking about completely different environmental conditions. Since we are dealing with moon, we have completely different range of temperatures, so we are going below 100 degrees and even above 100 degrees. So this is of course a big challenge for us to develop sensors inside the cone that are capable of measuring strength and penetration resistance into the soil.
I design systems that integrate sensors for geotechnical applications, i.e. Measuring different pressures in extreme environments, measuring displacement, measuring loads on very complex equipment and systems, mainly offshore, but also for soil lab conditions and systems. It's a big challenge with how we're going to instrument this CPT chamber, but with our knowledge from the soil lab and offshore projects that we've had to work on, we can pass on a lot of this knowledge into this current project to help us deal with these extreme environments.
Yeah, so we've made a test chamber for a CPT rig, as probably mentioned, and this is kind of similar to stuff we've done before for both the offshore market, onshore market, and especially our laboratory. We make these kinds of systems for in the workshop, and the instrumentation department designs them usually whenever the need arises. The special thing about this one is that it's to mimic the lunar surface, and the complexity in that makes it, considering the vacuum and the temperature ranges we're working with, makes this a lot more challenging, both in the ways of how we think mechanically, and especially when it comes to materials.
If you imagine it's going to be a chamber of these dimensions, or these shapes at least, and then we are going to be cooling down from the outside while removing the vacuum. And at the same time, we're going to be putting a piece of equipment called a CPT test and pushing it inside the soil. By doing so, we will find out how is the density, how is the strength parameters, how is going to be the lunar soil conditions on there, so that we can literally do much more safer economically as well the infrastructure on the moon.
I got the chance to investigate a very cool material, which is a sintering block of regolith simulants. We want to see by continuous displacement how much abrasion can happen, and also how that will affect the shear strength of the material. So the method we are using is the interface shear box, and this is the device that we are using. So it has a very simple principle. Basically, we put this block of regolith in the machine, and then we place a regolith simulant on top, and we shear continuously by moving the device front and back. In that way, we can see how much resistance will show, and we can use that to see how those two materials interact with each other.
I guess the main question is why we are doing this. So the main target for this is to, of course, be able to correlate these measurements of resistance to penetrate into the soil with soil mechanical behavior.
Some days.
So we're at the NGI Soil Mechanics Laboratory in Oslo, and now I'm sitting in front of the ring shear device. So ring shear device is a testing equipment, and this is actually built in-house by NGI, by our own staff.
Measuring geotechnical properties on the moon has lots of implications. There's a lot of interest in understanding how we're going to do things like engineering and building on the lunar surface. And just like here on Earth, before we start any of the construction or the excavations, often we do what's called a site investigation, where we try to characterize the strength of the soils, how they're going to deform when you put a load like a building on top of them. And on the moon, we know a little bit from the Apollo missions and the Luna missions, but we actually have only sampled a very small portion of the lunar surface. The idea with this chamber is that we're going to have a tool here on Earth that allows us to calibrate and test these very important geotechnical tools that may someday be used on the moon to help us build safe and long-lasting infrastructure. These projects are so complex that they often require a lot of collaboration, both internally across different groups at NGI, but also externally with partners either in Norway or outside. And in this particular project, we've partnered with a vacuum facility or vacuum company based in Poland, who's helping to design the big chamber that then our small cone penetration chamber sits inside of. And it's very essential that we have these kind of collaborations, because NGI could definitely not pull this off on our own.